We want to address this section 38.2 that's in our chapter on general relativity and astrophysics. This is called the elevator experiment. It is a classic type of what is called Gedanken experiment or thought experiment. It means you don't actually go out and do the experiment, but you pretend that something is occurring and then look at what that would imply. Well, Einstein compared an accelerated elevator to the same one in a gravitational field. Let's imagine we have an elevator here, section 38.2. This elevator has a hook on the top, and we can think of this elevator in two situations. One where it's just sitting here, and we feel the force of gravity, or the acceleration due to gravity, pulling it down. As you know, every mass, no matter what it is inside this elevator, falls with the same acceleration inside this box, which is not moving, simply due to the Earth's gravity. Here we can imagine the Earth here. Now I want to imagine another experiment, another elevator, and there's no Earth there, but in fact this hook is being accelerated upwards, so the whole elevator is accelerating upward with an acceleration equal to g. The question that Einstein asked is, can we distinguish the elevator that has an acceleration of g with an elevator that's sitting still but feels gravity? Now the key here is the fact that every mass falls toward the bottom of the elevator with the same acceleration. Likewise, if the elevator accelerates up, each of the masses in here seems to accelerate toward the floor and will accelerate toward the floor at the same rate. Can we distinguish between gravity and acceleration? Gravity over here and just acceleration over here. Well, if we stop and think about it, ordinary matter is not going to make a difference one way or another. It's going to appear the same. But if we took a beam of light in each one and sent that beam of light through a hole, and it goes over here in the elevator that's sitting on the Earth, since the photons have no mass, then they are not attracted to the Earth, and they will go straight across the elevator. Over here, if we send photons in through a hole, as these photons go over, the elevator itself is accelerating, so they will appear to move down here, so the beam will be bent by a certain amount. It says, well, okay, we can tell the difference then between the two. But Einstein said, he argued that by symmetry, since it's true for every particle here and every particle here, no matter what the mass or how small, and they all behave identically, and you can't tell the difference, he conjectured that light would be bent in the gravitational elevator by exactly the same amount that an accelerated elevator would present. Well, this violates Newton's formula for gravity. And the Newton's formula, you recall, is force is equal to g m1 m2 over r squared. And if this is the Earth, we make this the mass of the Earth, and this is the mass of a photon, a light, it is 0, and our force is 0, therefore. So it violates Newton's law of gravitation and says this law is wrong. His prediction would have to be tested some way to see if light got bent in a gravitational field. This is a very small effect. And so what he began to look at was light from a distant star. Well, what can we use to bend the light? Well, we could take this light coming toward us and say, let's let the sun be here. And then as the light came by, it would be bent. And if the Earth is over here, and the sun is here, we would be able to see this deviation, and the star would appear to be over here at a different place by an angle theta. Now, since we know where these stars are, then the fact that this star is actually back over here, we'll know it's here, and we can say, oh, it's now appearing to be here, and therefore it is shifted by this angle, and we can test this. But now we run into a problem. the sun would bend this light, and Einstein did this calculation and showed that that would be enough to detect it. In other words, the starlight from a distant star would be bent. But, however, he concluded that we could not see the star when it was near the sun. So we had to find some way of blocking the sun, and that was done by waiting for an eclipse where the moon was in the way, and we had a solar eclipse, and therefore the moon was entirely shadowed by the earth. The sun was entirely shadowed by the moon, and therefore we would be able to see the star. Well, this was verified that it was true, and we concluded it was one of the most famous experiments in all of history. One concluded that gravitation does bend light, and since gravitation bends light, it means that a straight line, which is defined by how light moves, may curve. Therefore, space itself must curve, since light curves in that space, and light is the measure of the shortest distance between 2 points, namely a straight line. So when we have matter somewhere, there's a star, then in fact the space around this is curved inward, almost like a piece of matter on a plastic sheet, and the sheet is weighted down here so that it makes an indentation in the center. And if we were to take something like a marble and roll it on the sheet, the marble would roll around here like this, and it would appear this marble was attracted to the sun when in fact it was only moving in the shortest distance, namely the curved space and time. Well, this is a very famous experiment, and there's no way to reconcile this with any type of normal way of thinking about gravitation, except to think that a theory of gravitation is a theory of acceleration, and a theory of acceleration is a theory of gravity, simply because all masses behave the same way in a gravitational field. Secondly, matter obviously bends space and time. So we're going to now look at the next section and see what that leads to in the rotating platforms.